In this video, we're going to look at an example of a problem involving stoichiometry with gases. Now, we've done stoichiometry before. The big difference here is rather than being given the amounts of reactants or products in grams, or in the case of solutions when we're given the concentration and the volume, in this case we're dealing with gases, and so we're going to use the ideal gas law to get into moles of things. So in this problem specifically, we're told that the compound KO2, or that's potassium superoxide, has been investigated for use as an air purifier in submarines because it reacts with carbon dioxide to produce oxygen gas. In the problem we're specifically interested in, we want to know if 355 grams of potassium superoxide reacts with 50 liters of carbon dioxide at 25 degrees Celsius in 1 atmosphere, what volume of oxygen can be produced? And we also want to know what is the limiting reagent. So the fact that it asks what is the limiting reagent is a dead giveaway that this is a limiting reagent problem. Even if it hadn't asked that, we know that it's a limiting reagent problem because they gave us the amount of 2 of the reactants. They tell us how much potassium superoxide we have and how much carbon dioxide we have. So I know that it's going to be a limiting reagent problem. So the plan of attack on this problem is I'm going to take the mass of potassium superoxide and I'm going to get that into moles. And then once I have the moles of potassium superoxide, I can get to the moles of oxygen by using the molar relationships in the equation. So I know that for every 4 moles of potassium superoxide, I'll make 3 moles of oxygen. And I'll do the same thing for the CO2. I'm given the volume, and I'm going to want to go to moles. Once I have the moles of carbon dioxide, I'll go to moles of O2, realizing that 2 moles of carbon dioxide will produce 3 moles of oxygen. Only in this case, for the potassium superoxide, I'm going to use the molar mass to go from mass to moles. In the case of carbon dioxide, because I'm given the volume and also the temperature and the pressure, I'm going to use the ideal gas law to get from volume to moles. And then once I figure out how many moles I can make, whichever one makes the least amount of moles, be it the carbon dioxide or the potassium superoxide, that's the amount of oxygen that I can make. The reagent that produced that much is going to be the limiting reagent. And then the problem wants to know what volume of O2 can be produced. So to go back to get the volume of O2 gas, I'll use the moles and the temperature and the pressure with ideal gas law to get the volume. All right, so let's go on to the next slide and start this problem. All right, so I'm going to start with the KO2 first. Now I'm going to see how much oxygen I can make from that. So I'm going to need to go from mass to mole, so I need to know the molar mass. And I've got 1 potassium plus 2 oxygens. When I add all that together, I get a molar mass of 71.10 grams per mole. So let's see how many moles of oxygen I can make from that. So I'm starting with 355 grams. I'll divide by the molar mass of KO2. And then using the coefficients from the equation, I know that 4 moles of KO2 will produce 3 moles of O2. And so when I multiply that out, the KO2 can produce 3.74 moles of oxygen. All right, so we've got room here, but I'm going to get some more room to go on to the next slide. I'll do the carbon dioxide, see how much oxygen I can make from that on the next slide. Okay, so for the carbon dioxide, I'm going to use the ideal gas law to figure out how many moles of carbon dioxide I have. Now, the pressure is good, that's in atmospheres. The volume is in liters, so that's good. But because I'm using R, I've got to be sure that I get the temperature from degrees Celsius into Kelvin. So I'm going to do 25 degrees Celsius plus 273.15. And to the correct number of significant figures, that's going to be 298 Kelvin. So rearranging my equation, I'm going to divide both sides by RT, so to get the number of moles, I'm going to do PV over RT. So let me go ahead and plug in my numbers. I've got 1.0 atmospheres times 50 liters divided by R and then times the temperature. All right, so if I check my units, let's see, I've got a Kelvin that cancels with a Kelvin. I've got a liters, an atmosphere, and an atmosphere. And I'm left with 1 over moles, or that's going to be in moles, which is good because I'm trying to calculate the moles. So that's what my units should come out to be. And when I do that, for the moles of carbon dioxide, to two significant figures, I get 2.0 moles of CO2. So now I'll use the coefficients from the equation and see how much oxygen I can make from that. So from the equation, I have 2 moles of CO2 will produce 3 moles of oxygen. So that's going to make 3.0 moles of oxygen. So if you remember from the previous slide, from the potassium superoxide, I could make 3.74 moles. So that means that I can actually only make 3.0 moles of O2, and my limiting reagent is CO2. So the last thing we need to do, the problem wants to know what volume of O2 can be produced, so we'll figure that out on the last slide. Okay, from the previous slide, we saw that carbon dioxide was a limiting reagent, and the moles of oxygen that I can make was 3.0 moles. So to get the volume, I'm going to use the ideal gas law. I want to solve for the volume, so I'll divide both sides by P. So the ideal gas law, I'll rearrange it to get volume is nRT over P. So I can go ahead and plug my numbers in. So I've got 3.0 moles times R temperature was 298 Kelvin. And I'll divide by the pressure, which was 1 atmosphere. So let me check my units. I've got a Kelvin and a Kelvin, a mole and a mole, an atmosphere and an atmosphere. I'm left with liters, which is good. That's what I would expect the volumes to be in a unit or something like that. And so when I divide all those numbers out to two significant figures, I get 73 liters. And that's our final answer.